SwayamPrabha. Digital India. Educated India.
Hello. In the previous video we discussed about the conditions for linearity to decide whether a particular material is a linear or a non-linear viscoelastic material. So, in this video we will introduce you with few phenomenological models. So, these are models which empirically match with the experimental observations, but they are not founded from first principles. So, what this means is this is all good for analysis of either polymers or viscoelastic materials, but these models which we will be discussing are not derived from first principles starting from observations of polymers. These only match the stress strain relationships, how a normal polymer behaves. So, as we mentioned, we will be first starting with the stress strain relations, and to describe these stress strain relations we will introduce few phenomenological models. A few cautions before we go ahead with these discussions. First, saying that it only captures a few aspects of polymeric viscoelastic behavior. What we mean is it cannot be used to capture real polymers, because real polymers have a much more complex phenomena which cannot be captured using at least simple phenomenological models. We will, in this course we will discuss both some elementary models as well as some advanced models which can maybe capture this behavior of real polymers. So, we start by introducing some elementary mechanical models which will be helpful to describe the solid behavior of a polymer and the fluid or the viscous behavior of the polymer. As the name says, when we talk about viscoelasticity, we should first able to describe the viscous behavior as well as the elastic behavior. So, to describe the viscous behavior, we use these linear viscous dampers. Since we are talking about linear viscoelastic, we focus only on the linear viscous damper to describe the fluid behavior, and for the solid behavior we focus on the linear elastic spring. In the following slides we will see how this spring and damper can be used to describe the viscoelastic behavior of at least simple polymers. So, let us get started with linear elastic spring. The analogy we have to look at is the Hookean elastic bar. So, what we are saying is we will take a elastic bar made up of linear isotropic material. Linear isotropic material, as we know, follows the Hookean behavior, which means stress and strain are directly proportional to each other. That is why we say we are following the Hookean elastic bar. But let us see what we mean by Hookean elastic bar and what is the kind of relation we get between stress and strain. So, what we say is we start with a uniaxial bar and then apply an uniaxial load. So, let us say we are applying an uniaxial load P on both ends. So, now let us say this bar has the geometry of length L, cross section A, and it is made up of linear elastic material of elastic modulus E. Okay. Since we are loading with a constant load P, under load it deforms. How much does it deform? Let us say it deforms by delta. Delta is the deformation because of the applied load P. So, from basic mechanics or basic solid mechanics where we discussed about the bars, we know for elastic bars this can be described as this deflection is PL by AE. Okay. So, now let us rearrange this such that now we can introduce the stress term and the strain terms. So, the way I will do it is I will keep this P by A on the right side of the equation and move the other terms. So, first delta I will divide it by L and I will bring this E to the other side and write it here. So, if I write it rearrange things in this fashion, now I have this term P by A. Load per unit area is what we discuss as stress, define as stress, is E times deflection, delta is the deflection per the total length, this is the strain. Okay. So, with this we show that the stress is directly proportional to strain and the proportionality constant is given by E. So, we are saying that this is the linear or the Hookean elastic bar, but the model we are using is a spring. So, now let us see a spring. So, this is the symbol we use to represent a spring. So, let us say we are applying a load P on both sides of the spring, and to start with let us say this spring has a spring constant of K, we are applying a load P. So, how is the spring constant defined? We know that spring constant P is delta by P. So, the deflection per unit load. Now, let us rearrange this such that we bring it close to the expression here, which we have for deflection in a prismatic bar. So, let us say I will take this P to the left hand side and then divide it by A on both sides. Similarly, I can leave delta here, but multiply and divide by L on numerator and denominator. So, now we have these three terms, P by A which represents the stress and delta by delta, delta by total length is the strain. So, now what we will do is we replace this fraction KL by A with E, and then we again get this Hookean law saying that stress is directly proportional to strain and the proportionality constant is E. So, what we are trying to show here is the spring can be used as an analogy to linear elastic solid behavior, where the example we have taken is the bar here. So, with this let us now look at the viscous behavior. Here we look at the linear viscous damper. First let us see what is a damper. Damper is a perforated sheet which is contained in a container filled with a fluid. So, let us say this is the container, and then we have this damper which is perforated. Perforated meaning let us say this is a circular damper or a sheet in circular cross section area, and then we have many holes in it, right. So, let us say we are looking from the side, so the holes are somewhere here, and then this is connected with a rod. Okay. So, what we say is of course this damper is closed and it is filled with a liquid on both sides of the damper. So, first we assume that this fluid we have filled is a Newtonian fluid. So, to explain this damper we will take an analogy of a plate which is resting on a fluid and then we move the plate with a constant velocity. So, let us say this is the bottom which is fixed and then we have this plate which is resting on fluid, and then this plate is moved with a constant velocity v, which is given as du by dt. Just du by dt, where u is the displacement of any point in this plate. So, what we see is at the bottom there is no movement in the fluid, but at the plate there is a velocity v or du by dt. So, how does the velocity vary? It varies linear. So, at the top it is velocity v, but as we go down the velocity decreases, and we discuss about no slip boundary conditions, which means both at the bottom and the top boundary there is no discontinuity in the velocity or discontinuity in the displacements. We can now apply the Newtonian law of viscosity. So, in this Newtonian law of viscosity, we consider an elemental volume. Let us say the initial shape is unit square, but then because of the shear forces it deforms. The shear stress is acting, let us represent it as tau xy. So, this has a vertical length of dy, and this deformation is represented with du. So, du is how much this vertical line of the elemental square we have shown deforms, or the rotation of it. So, the shear strain which is shown with gamma is given as du by dy. Okay. So, now coming back to the Newtonian law of viscosity, what it says is the shear stress tau is given as viscosity mu times time derivative of du by dy. So, what is du by dy? It is simply the shear strain gamma. So, we can simply write it as shear stress is viscosity times the strain rate. We represent it with a dot at the top of the shear strain gamma to represent that it is the first derivative with time. So, this should give us the Newtonian law of viscosity relating your shear stress with the shear rate. So, to bring it close to the analogy of spring, where we write in terms of stress is sigma and for the strain we use epsilon, we will replace shear stress with sigma, we will retain the viscosity mu, and we will replace the shear stress with gamma with epsilon with a dot, because it is a time derivative. So, this is the formula we will be continuing to use whenever we use a damper or the stress strain relation between the stress and strain rate for a damper. But essentially what this is representing is the stress is directly proportional to the strain rate. Bear in mind, this is very different from what we have seen for a solid, where we said stress is directly proportional with strain and the proportionality constant is E. So, this we will say it for solid, and the previous one is for viscous flow. So, if you notice both these equations, we now see the difference between a solid behavior and a viscous behavior, at least in the linear sense. So, in solid, stress and strain are directly proportional to each other, whereas in a viscous fluid, stress and strain rate are proportional, and that proportionality constant is viscosity for fluid, proportionality constant is E or modulus for solid. So, now we have defined how a linear solid behaves as well as how a linear fluid behaves. Okay. Now, let us use these concepts to develop some models which can be useful in defining or explaining the behavior of viscoelastic materials, or in our case polymer behavior. So, there are many ways one can think of by which one can combine both the spring and the damper and come up with new models. But we will start with very basic models. We will start with what are called as Maxwell and Kelvin models. So, in the Maxwell model, we take one spring, one damper and connect them in series. So, let me show. So, we have one spring here which is in series with a damper, and this is the Maxwell model or the Maxwell element. So, we represent this spring with modulus E and the damper with viscosity nu, and at the ends we apply stress or strain, and if we apply stress, the response is the strain, and if we apply strain, the response is stress, right. Okay. So, in contrast, we have also Kelvin model. So, the only difference between the Maxwell and Kelvin model is Maxwell both spring and damper are in series, now we will show them in parallel. So, we will represent the spring again with E and the damper with viscosity nu. And at the ends of the model we have the stress and strain, one as input and the other as the output. Okay. Now, let us try to understand how would a Maxwell model behave and a Kelvin model behave. Here I am not trying to go into the equations, but trying to understand how can we relate these with polymer structures we have discussed, and also to see which of these models are good to model either a thermoplast or a thermoset. Okay. Now, let us focus on Maxwell model. Maxwell model, we say that it has a free spring and a free damper. Let me first write it and then explain you what a free spring and a free damper means. What we are saying is these are not in parallel with any other element. So, if I look closely at the spring, it is in series. So, there is no other element in parallel. So, the reason why we are focusing on this free spring and damper is it explains what happens when at the instant of the load, which we defined as initial response or the instantaneous response, and it also defines how this Maxwell model behaves at long periods. So, if we wait for very long periods, which means t tends to infinity, how the model behavior looks like. So, let us understand with again creep and relaxation test. Let us say we are discussing about creep, load. So, in creep test, what is our input? We said the stress is simply constant, which is sigma naught. Okay. Now, you should be able to think and answer what is the initial response of it. So, we said we apply an instantaneous load, right, that is the definition of creep. We are talking about stress versus strain. So, at time t equal to 0, there is a sudden increase in the stress. So, how would the strain look like in terms of the spring and damper? Will it have any instantaneous value or not is the question. So, the answer is it will have an instantaneous strain. But which of these element is responsible for the initial strain? So, will the spring respond instantaneously or the damper respond instantaneously? We know the spring will respond instantaneously because that is what elastic solids do. When I apply a load to a aluminum bar or a steel bar, the response is instantaneous, but with a damper it is not the case. With the damper the deformation is gradual because of the formula we have. So, where we said the stress and strain rate are proportional, it is not the stress and strain which are proportional. So, which means this instantaneous strain is because of the free spring. Okay. So, one way to represent this is saying that at time t equal to 0, the strain is not equal to 0. So, which means there is a instantaneous value. And what about the equilibrium strain, or if we wait for very long times, how will that strain look like? So, now we are talking about time tending to infinity. So, the answer is, let us think about each element at a time. For the spring, right, there is an instantaneous deformation, and after that there is no more deformation. So, even if you wait for a long time, since the load is not changing, the strain also will not change. But if we think about the damper, initially there is no deformation, but once you give it enough time, it keeps deforming. And will it stop? No, because the deformation is or the stress is proportional to the strain rate. So, which means it keeps on elongating. So, the answer here is the strain will go to infinity if we wait for long periods. And now you should ask a question, which of the materials will behave like this, whether it is a thermoset or a thermoplastic. So, from earlier discussions we know thermoplasts are the ones, if you apply a creep load, the deformation goes to infinity. If you recall previously for creep, it was something like this. So, for thermoplastics it goes to infinity, but for thermosets it reaches to a constant. So, what we are saying is this matches well with thermoplastic. Okay. Now, let us look at relaxation loads. So, in relaxation we know the input is strain. So, the strain is constant epsilon naught, and how is the response? So, which means we have this Maxwell model, we applied an instantaneous strain and we are holding it, and now we are measuring how does the resistance stress varies. So, initially we get stress because of again the spring, because the spring is the one which gives all the instantaneous deformation you give. The damper will not budge initially, which means it will just there is no strain from the coming from the damper, all the strain is coming from the spring. Okay. That is what happens at time t equal to 0. But now that if you give enough time, that is when the damper is giving elongation. So, when the damper is elongating, it is eating up or being compensated by reduction in the displacement of the spring. So, which means the deflection in the spring and the damper should remain constant, right. So, as the damper deformation increases, the spring deformation decreases. Okay. So, we said for relaxation, what happens if we wait for long times? What happens? So, if we wait for long time, we said the instantaneous deformation is because of the spring, but this damper will give back all the deformation to the spring, which means the spring will go back to its initial state. When the spring goes back to the initial state, the damper is also free to move. So, there is no resistance coming from the damper, because this initial stretch is taken care by the damper, and you have given enough time so that it has readjusted and gone back to 0 stress state. So, which means stresses as time approaches infinity goes to 0. Now, we should ask this question, whether a thermoset does like this or the thermoplast behaves like this. The answer is it is the thermoplast which behaves like this, because we said thermoplast, the molecules can slide over each other, which means even if you are given a stretch, if there is enough time, they flow, and once they flow, there is no resistance. So, again thermoplasts are the ones which represent the behavior of relaxation for a Maxwell model. Okay. Now, let us move into the Kelvin model. Kelvin model, we first notice that there are no free spring nor damper. Okay. And now, let us start discussing about the creep response of this Kelvin model. Creep, again we know that we apply an instantaneous stress, and we are looking at how the strain changes. So, now that the spring and the damper are parallel to each other, when we apply a load, initially there is no deformation. Can you think of why there is no instantaneous deformation? Meaning that the strain at time t equal to 0 remains at 0. The reason is because even though you have applied a load, as we already have seen, the damper never shows you an instantaneous deformation. So, the damper will not budge initially. Since the damper will not deform, spring also cannot deform, because both of them should maintain the same deformation or strain. That is the reason why the instantaneous strain is 0. But the next question is, what happens when we wait for long time? So, when time approaches infinity, that is when the damper, as we wait, starts to move, but then it cannot go to infinite strain, because what is stopping the damper to go to infinite strain? That is the spring. Spring, as we know, for a particular load it can deform, right, but it cannot deform more than that. To deform more than that, you need to apply more load, but we are not increasing the load, right. The kind of test we are doing is we applied a fixed load, which means the deformation increases until the spring is stretched to the corresponding amount of strain, and then it remains constant. So, which means if we wait for long times, it reaches a constant value, and this constant value depends on the spring and not by the damper. Okay. Now, let us come to a very interesting experiment or an observation we will have. So, now let us think about a relaxation test being conducted for a Kelvin model. So, we are saying that okay, this is the Kelvin model and then I need to apply an instantaneous deformation. First of all, the question is it possible to apply this or not? The answer is no. You can't apply an instantaneous deformation for a Kelvin model, no matter how strong you are or no matter how strong machines you are using. The reason is simple, because we have been repeating this often, saying that the damper won't budge instantaneously. If you give it time, it will give deformation, but if you say I want to force it to have instantaneous deformation, you really need infinite load. The answer is simple, because earlier we have seen what is the how does a damper behave. We said stress is proportional to the strain rate, and when we are saying relaxation where we apply instantaneous strain, what is the strain rate? The moment we say instantaneous strain, it means the strain rate goes to infinity. So, when you expect that the strain rate is going to infinity, what does this formula say? It says that the stress needed for this is also infinite. So, since we cannot develop any machine which can apply an infinite load, the simple answer to this is not possible. So, we cannot conduct a relaxation test with a simple Kelvin model. The sole reason is because we have a damper which cannot take instantaneous strain. Okay. I hope this gives a clear picture about what are Maxwell model and Kelvin models and how they are different. One point I forgot to mention is, now let me pose this question: which material you think is closely behaves like a Kelvin model, whether it is the thermoplast or the thermoset? So, looking at creep, we said okay, if we wait for longer also it should come to a constant value. Earlier I have shown you already. So, thermosets are the ones, even if you wait for very long times, there is no change in the corresponding strain. So, it reaches a constant value. So, the creep test very well represents the thermosets and not the thermoplastics. Okay. So, these are, though these Maxwell and Kelvin models are so good, these are very simple, basically meaning that it is hard to expect that we can use any of these models to represent any real polymers. So, the way to do it is, now we need to add more springs and more dampers. So, as we add more springs and dampers, then that brings in the required complexity or the required reality, so that we can match it or come close to a real polymer. Okay. But since again we have the limitations of time, we will again focus on very basic models. Two other additional basic models we will focus are the 3-parameter model and the 4-parameter model. First, let us look at how we arrange these springs and dampers to get the 3-parameter model. The way we do is, we take a Kelvin model and we attach in series a free spring. So, which means we start with the free spring and then we attach a Kelvin model. Kelvin model meaning spring and damper are parallel to each other. Okay. So, to differentiate the two springs, let us call the free spring as E naught and the one in the Kelvin model as E1. the corresponding viscosity is nu 1. Okay. Again we either apply stress and measure strain or the other way. Okay. And now yeah, there are of course other possibilities when I say a 3 parameter model, meaning like one can always come up with other combinations, saying that probably there is, instead of a free spring, now you have a free damper. Nobody is stopping us from doing it, but what I am trying to show is something which is more commonly used. And for a parameter 4 parameter model, it is pretty much close to the 3 parameter model, the only difference being that in addition to this, now we have a free damper. So we have the free spring and then the Kelvin model and then a free damper. So we will represent the free spring with E naught and the free damper with mu naught, and the springs are for the Kelvin model, these are E1 and nu 1. Okay. With again the inputs and outputs as stress and strain. Okay. Now let us look at a 3 parameter model. We said that it has a free spring, it has a free spring element. So because of this free spring element in series with a Kelvin model, now the behavior is slightly different. So let us again look start with creep loads and see how it behaves. Okay. So creep load meaning there is an instantaneous stress, and now we are looking at instantaneous response of strain. So what would be the strain response be at time t equals 0, or the instantaneous strain? The answer is we do have an instantaneous strain, and all this instantaneous strain is coming from the free spring. Okay. And the other extreme is now how does it behave when we give plenty of time. So when we wait for a very long times, then the free spring has instantaneously deformed and it stays there. There is no further deformation. But the Maxwell model which is embedded in this 3 parameter model, right, instantaneously there is no strain, we know, because the damper will not budge, but then given enough time this damper will start expanding. When the damper expands, it will also let the spring E1 also take the deformation. But if we are waiting for long times, then there is no more deformation possible with E1, because it reaches a value by which it reaches the maximum deformation for a particular load. It can deform no further if there is no change in the load. Since we are talking about creep load where the load is constant, the spring E1 can only deform to a particular extent and then stop. So which means even in this case it is non-zero, and we should also say that it reaches a constant value. Okay. So again, if I ask whether this represents a thermoplast or a thermoset, the answer is it represents a thermoset. Why do we say it is a thermoset? Because we said that if we wait for even longer times, we do not get infinite strain, we do get a finite strain, and that represents well for a thermoset. Okay. Now let us move on and look at what is the relaxation behavior. So, we know that relaxation means instantaneous strain is the input. So, will it have any instantaneous stress as the output or not? The answer is it will have instantaneous stress, but all the stress is coming from again the free spring, because the free spring will let you deform based on the how much strain. So, depending on the extent of the strain, it will deform, and then there is a corresponding resistance stress. So, which means at time t equal to 0, it is non-zero. Okay. But now the question is, if we wait for very long times, how will it behave? So, we said we stretched and we are waiting. When we wait, what happens is this damper gradually deforms, but then after a while it stops. The reason why it stops is again the spring will not let it deform for infinite extent. So, which means there is a finite amount of strain, both the springs E0 and E1 take, and then they stop. So, which means when t approaches infinity, you reach a constant value or a finite value of stress. Again, this behavior matches well with a thermoset and not the thermoplast. Okay. Now that we have discussed about the 3 parameter model, now let us focus on the 4 parameter model. As we have seen, the major difference is we have both a free spring and a free damper. Okay. So, now again let us see what happens when we apply creep load. So, once we added this dead weight, instantaneously there is deformation, and that deformation is because of E0. Strain at time t equal to 0 is non-zero, and that is because of E0. But then what happens when we wait for very long times? If we wait for very long times, that is when the free damper comes into play, because the free damper is free to elongate by any amount depending on how long you wait. So, at time t approaching infinity, we reach infinite strain, and this is mostly because of the free damper. Okay. So, initially there will be some nonlinear behavior meaning the relation between strain and time, not the stress strain. That is because of this Kelvin model being here, or this E1 and nu1 which are parallel to each other. And we are saying this plays well with thermoplastic or a thermoset. We have seen that this plays well with a thermoplast, because in a thermoplast if we wait long we see infinite strains. Now moving into the relaxation behavior. Now if we apply a constant strain, that instantaneous strain is taken by the free spring. So which means the measured stress at time t equal to 0, which is non-zero, and it is mostly because of the free spring. But the question now is, what happens if we wait for long time? So we stretch it by a fixed amount and we wait long times. When we wait long times, what happens is all the strain applied can be taken by this free damper. So the springs E0 and E1 can go back to their original shapes or the original initial deformations, which is 0. So the stress as time t approaches infinity is 0, and this is mostly because of the free damper. And again which kind of material exhibits this behavior, which is a thermoplast. Thermoplasts are the one if you apply a fixed strain, instantaneous strain and wait for longs, the stresses again go back to 0, and all because again because of the molecular structure where the molecular chains can slide past each other given enough time. So, with this we will be concluding this video, where we have discussed about few phenomenological models. We started with the basic linear elastic spring for a solid and a linear viscous damper for a fluid. And on this slide we have shown two slightly more complex models than the basic Maxwell model and the Kelvin model. In the Maxwell model we have the spring and damper in series, Kelvin model both of them are parallel. So, but that cannot be used to really represent a decent viscoelastic behavior. That is when we need more springs and dampers in the model. So, in that perspective 3 parameter model and 4 parameter model are commonly used to represent decent strain, but of course even this is not equal, even this is not sufficient to model a real polymer. Usually in real polymer, in reality what people do is they have either a series of Kelvin models in series, or we have multiple Maxwell models all in parallel. We will discuss all of it in the coming video. Thank you.